let me make an announcement about the forum. So I think most of you, maybe all of you, signed up already. I'm sorry that it was a little bit bumpy for the first couple of days. It kept crashing on you. But I think it should be working now. And I will approve your request today. So maybe right after class, I'll go do this. So maybe in about an hour, you guys can already log into the forum and participate in everything. And you guys in Colombia are already set up because I did that already. Okay. So let's keep talking about Coxeter groups. Last time, I told you what a Coxeter group is. I told you that it's a group that is generated by some set of generators subject to some relations. And the relations are all of the form Si Sj raised to the power m sub m of I comma j equals the identity. So that's what a Coxeter group is. Now, this is a definition, but let me start today by telling you a disadvantage of this point of view so far. I think maybe some of you have seen this point of view on group theory. You can describe a group by saying, I give you some generators, and I give you some relations. Maybe some of you have seen this. Maybe for some of you, it's the first time that you think about a group in this way. It is possible to present any group in this way. But the point is, what you should be asking yourselves is how useful is this presentation? And the first thing that I want to tell you is that, in general, this kind of presentation of a group is very difficult to work with. Okay, so it's hard to obtain information about a group if we know just one of these presentations from a presentation in terms of generators and relations. And this isn't just a subjective word, hard. Let me tell you why this is hard in general. You might ask yourself, okay, let's say that I'm given a group, I'm given some generators, I'm given some relations. Then the very natural question is the word problem for a group with a given presentation. And the word problem is basically, I'm given a word in the generators, given a word in the generators, the word problem is to determine whether this word is the identity element or not. Okay?
That means a word in the generator, that means the word is made up of all generators.
Exactly.
So, string of generators.
So in this case, I might tell you S1, S3, S7, S2, S4, S3, S2. I give you some long word and I ask you, is this the identity or not? Well, this should be I mean, you would think this is a very natural question that we really should know how to answer. And the point is that actually this important question is very hard in general. It's so hard that actually no algorithm can do it for a general group. So this is undecidable. That's the technical word. Undecidable, meaning that no algorithm can do it for general groups. I don't want to go into technicalities. If you want to know exactly what this means, you should go into go ask Wikipedia what undecidable means. But the point is that no algorithm can solve this question in general. And so we're going to want a different perspective on Coxeter groups if we really want to understand them. Okay? And one thing that we will be able to develop after developing some theory is that actually this is decidable for Coxeter groups. But that's only because we understand a combinatorial structure on Coxeter groups. So decidable for Coxeter groups, but only after we develop some theory. Need more theory. Okay? But hopefully this convinces you that really this presentation is not sufficient for us, and we really want to develop some more concrete ways of thinking about Coxeter groups. And so that's the next thing we're going to do, is we will develop two concrete ways of thinking about Coxeter groups. Two concrete realizations of Coxeter groups. One is combinatorial, so I'll show you a way of thinking about a Coxeter group combinatorially. And the other one is geometric. We will see that you can think of any Coxeter group in a geometric way. So today we're going to do this first one. We're going to realize combinatorially a Coxeter group. And the second one we will do in a few weeks. This will take some time to develop. Now, what should you have in mind about what we're going to do today? You might remember this very beautiful theorem from group theory called Cayley's theorem, which tells you that if you have just some abstract group, you don't know anything about it, well, it turns out that that group you can find inside a symmetric group. In other words, there's a subgroup of some symmetric group that is isomorphic to your abstract group. And that tells you that this abstract notion of a group you can think about very concretely as a group of permutations. That's what we're going to do today, except we're going to do it a little bit differently. We'll realize W as a group of, not of permutations, which is what Cayley's theorem does, but as signed permutations. And this will let us think about this group more concretely. Okay? So this is the plan for today. This is what I'm going to do today. So that should be the first thing I do. I'll tell you what I mean by signed permutation. So let's talk about that first. Let me teach you a very long word. Hyperoctahedral group. Okay? This group is denoted like the symmetric group, except that it has a B here, SNB. This is the group of signed permutations. So what is a signed permutation? Well, what it is I think it's clearest in an example. So here's a signed permutation of 7. 1, 3 bar, 6, 2 bar, 4 bar, 7, 5. So this is all a signed permutation is. It's a permutation of the numbers from 1 to n, except that some of them are deemed to be negative versions of the number. So they come with a sign that is either positive or negative. Okay? You can think of this as So this is the example. You can think of this as a permutation of the set 1 up to n and minus 1 up to minus n, such that the permutation of minus I, the permutation entry of minus I is minus the permutation of I. So from this point of view, the way I'm thinking about this permutation is saying pi of 1 is 1, pi of negative 1 is negative 1. Pi of 2 is negative 3, pi of negative 2 is 3, etc. So same thing. You'll see it described in this way sometimes. And a nice way of thinking about it is, we talked about how we can think of the permutation group as shuffling cards. Okay? Well, we can think of the sign permutation group as shuffling cards, except that each card has a top and a bottom, and we're allowed to flip. So we can think of this as shuffles of a deck. So here's my deck. It has n cards, and each card has a front, 1, and a back, negative 1, 2, negative 2, n, negative n. And all I'm doing is shuffling these in every possible way. Okay? And then this also describes to you what the group operation is. You just shuffle according to the one permutation, then shuffle according to the other. Okay? I'll actually multiply explicitly in a second to make sure that we understand. But so those are the sign permutations of n. They form a group by composition of these shuffles. And I think this is also an exercise in the homework, is to show that this is also a Coxeter group. SNB corresponds to the Coxeter diagram, where you have n nodes labeled S1, S2, S3, up to Sn minus 1, which are the usual flips of the ith and the ith plus first card. And then this other one, which we might call T, and this corresponds to just flipping the top card. Okay? So this is the transposition of I and transposition of 1 and 2, etc. 1, 2, this is the transposition n minus 1, n. And this is the transposition between 1 and negative 1. So it flips the top card. So this is the Coxeter group of this Coxeter diagram. Okay? And this means that this gives me another description of this group in terms of generators and relations. Okay?
Federico, the 1, 2 means you take this, the first card and make it the second card. If you reverse the order of the first and second.
No, so I should say, so what this means is you take the first and the second card, and you just switch their positions without flipping them over. Okay? So if you use only these n minus 1 operations, then all of the cards are going to face the same way. And this operation allows you to take the top card and flip it over. But then if you want to flip one in the bottom, you just bring it to the top, flip it over, and bring it back to the bottom. Okay. So this is what a sign permutation is. And now my plan is to show you that actually we can think of any abstract Coxeter group as living inside one of these. I'll show you how to do that. So this is the signed permutation representation of a Coxeter system given by a Coxeter group and a presentation of it. This is the thing I want to describe today. Okay? So again, given WS. My goal is to find a copy of it inside some hyperoctahedral group, which, let me just denote it by T. This is supposed to be some set, and we're just going to consider the sign permutations of that set. Okay. This is my goal for today. So let's do this in 3 steps. First step. The input that I'm given is W and S. You can think of this as also, I'm just given a Coxeter diagram. It's the same information. And my goal is to find it inside some hyperoctahedral group. And the first thing I want to decide is what is this T? Yeah? What are the objects that I'm going to be permuting? That's the first question. Now, one thing I should say, I'm going to first describe this to you abstractly, and then we'll do an example of how this works. Okay. So the T that I'm going to use is going to be given by the following set. It's going to consist of the conjugates of the generators inside my group. Okay. So these things are called the reflections. In fact, maybe what I'll do, let's do this in parallel. So let me first describe abstractly what I'm going to do, and then we'll do it in an example so you see at each step what it is that I'm doing. So let's see, what can I erase? Let me just do a little bit of Blackboard planning here. Let's go here. So my example is going to be W, well, the one that we understand very well. S3 with generators A and B. Okay. So remember that A and B are switching 1 and 2, switching 2 and 3. So T consists of the conjugates of A and B in the symmetric group. Now, remember what the conjugates in a group are? They're basically the elements that kind of look the same and behave the same way. I really suggest that if you don't remember this very well, you should go back to your notes from your algebra class and remember this. But basically, they're the elements in the group that kind of play the same role as these. And what are the conjugates of this guy and this guy in this group? Well, first of all, every element is conjugate to itself. So these two are in here. And what else? ABA, which is, if you do it, it's 1, 3. Okay. Now, why should we think of this as ABA? Well, because we're thinking putting W, then one of these guys, and then W inverse. So for example, I could put in W equals A, then this one, and then A inverse, which is, again, A. And so what I get is ABA, which is 1, 3. Okay? Now, you can really do this by hand if you want. So I'm going to call this guy A, this guy B, this guy C, and you should really take the time to convince yourself that these are the only conjugates of A and B. Okay? And let's also record here that C is equal to ABA, which is equal to also BAB. Okay? So what I'm saying is that now I want to think of this group W as living inside the signed permutations of this set A, B, and C. So I'm going to realize each element in here as a signed permutation of these three guys. That's my goal. Okay. So now let me tell you where can I find this guy inside here. In other words, over there I have the 6 permutations of S3, and for each one I should be assigning one signed permutation of T. Okay? So in general, what I need to do is, given each one of these generators, I need to decide where I'm going to send it inside here. Okay? And given any element of my group W, I want to decide where that element lives inside here. Okay? So let me tell you how to do that. Let's take a generator of my group W. Now, I need to define a signed permutation that corresponds to it. Signed permutation sub S. So what that signed permutation does is that it switches around this set T. In other words, I need to tell you what it does to an element T. Okay? And it should send it to a different element, or maybe the same element, but it should send you to some other thing in T, possibly with a minus sign. Okay? And what it's going to do is that it's going to send you to plus or minus S, T, S. Okay. Now, how do you decide if it's a plus or a minus? Basically, it's going to be a plus always, except it's going to be a minus when you plug in S here. So plus if T is not S, and minus if T is S. Okay.
So I forget, the S's are generators, and the T is not necessarily a generator.
Exactly. So I'm thinking of S as an element of my set big S, and T as one of these reflections. And so pi sub S should permute my reflections around, possibly with signs. Okay. So we should go ahead and do that here, and really do this concretely. So I'm going to define, here's an element of W, 1, 2, and that defines for me a permutation pi sub A of T, which might have signs. Okay. Now, that equation over there tells me how to define pi sub A of A, pi sub A of B, pi sub A of C. Yeah? So, and all I have to do is just plug in what that says. So what's this? Well, first of all, I told you what the sign is. The sign is minus when these guys match and plus otherwise. So this is minus, this is plus, and this is plus. Okay? And then all you have to do is do that I wrote over there. So this is AAA, this is ABA, and this is ACA. Okay. Now, there's something that maybe is not immediately obvious to you, which is that what I'm supposed to get here are elements of T, right? Because pi sub a is supposed to permute things in T. So if I plug in things in T, I should get things in T. So hopefully when we compute this, we get things in T. So let's go ahead and compute each one of these guys. AAA, well, we know that here a squared is the identity, so this is just minus a. ABA is C. What about ACA? Well, ACA, we know that C is ABA. So we can plug that in, cancel AA, cancel AA, and I get B. Okay? And so you see we actually did get a signed permutation of A, B, and C. T is A, B, C. And a signed permutation is just a way of assigning to each one of these guys, I mean, a permutation of A, B, and C that comes with signs. That's what I did. Okay. So that means that pi sub A is the permutation which, in the notation that I just erased, we can write this in one-line notation as minus A, C, B. But just so it's a little bit more concise, we write the minus on top. Okay. Now we did the first one slowly. Let's do the second one quickly. I think we can do it. Pi sub B. So what does that do? First of all, the signs say that you're only going to get a negative sign on the B entry. So we know that it's positive, negative, positive. Okay. And here I'm going to get BAB, BBB, BCB. BBB is B, BAB is C, BCB is A. Okay. So I just compute this, and that's what I get. So that's going to tell me that the images of A and B inside this hyperoctahedral group is A is going to go to this sign permutation, B is going to go to this sign permutation. That's the first thing. Okay. Now, there's a question mark here, which is, first of all, why does this all land in T? Second of all, why is it a permutation? Okay. And we'll prove these things. But at least in that example, you see that they're true. So this tells me what pi sub S should be. But now I have to also, I have to map the whole group W inside the sign permutations of T. So it's not enough to map A and B. I have to really find an image for each one of these elements of here. And so the question now is, if I give you some element of W, how are you going to map it to a permutation of T? And there's one natural choice, which is that because you can write any element of W in terms of A's and B's, you just take the same expression, except you plug in pi sub A's and pi sub B's. So that's the plan. If I take now pi sub W and T, then if I want to figure out what the permutation pi sub W is, all I'm going to do is write W in terms of generators, S1 up to Sk, and then just write the same word, but actually let me just get rid of the T. I don't need the T here. Pi sub W is just going to be the composition of all of these sign permutations. Okay. So let's do that in this example. I already defined the images of A and B as sign permutations, but now I need to define the images of pi E, pi AB, pi BA, and pi ABA. Okay. When I do this, I'll have images for all the groups and for all the elements of W. Well, there's one that's easy. E is the empty word, and so that means that I should just get the identity here. Now, these two are medium, and this one is a little bit harder. And there's a reason why this one is a little bit trickier. If someone worried about this, you should be worried about this, because I had two choices here. I could call this element ABA, or I could call it BAB. And this gives me two different formulas for this element. Yeah? I mean, I can write this as pi A, pi B, pi A, but I can also write this as pi B, pi A, pi B. And we should be a little bit worried, because that means we have to operate these permutations, and we might get different answers here. Yeah? Well, you shouldn't be too worried, because I wouldn't go this far if we weren't going to get the same answer, right? But maybe we should talk about how you actually do these operations in an efficient way. Well, it turns out that we can also think of these guys as these wiring diagrams in a very natural way. ACB, we just draw this wiring diagram for A goes to A, B goes to C, C goes to B. The only thing is that we need to indicate what's negative and what's positive, and so we do that. So what I do is that let's make it a blue to mean that it's negative. Okay? So this is pi sub A. And pi sub B, what it does is that it sends A to C, C to A, and B to minus B. So we make it blue. And then we just operate in the same way, it's just with colors now. Okay. So what's pi A, pi B, pi A? Well, we just have to stack three of these pictures, right? So I won't spoil you the fun of this, actually, again. So you should really, let's do one, and I'll let you do the other one. So pi A, pi B, pi A. So you put A, then B, and then A. And then you just see what got wired to what. So the first guy got sent to the second guy. So that's a B. And it has one blue. So that means that it should be negative. The second guy got wired to the first guy, and it should be negative. And the third guy got wired to the third guy, and that should be negative also. How do you deal with these colors? Well, we're basically, if you see an odd number of minus signs, then that's negative. And if you see an even number of minus signs, then it's positive. So you should really do BAB and make sure that you get the same answer. What about AB and BA? Well, you can read them off from here, because this is AB and this is BA. So you just read that off, and you find that they are, where did they go? B, A, C, and C bar, A, B bar. I'm sorry? Question?
I was just wondering, why don't you think of the last two as pi of c? And account.
I do think of them as pi of c, actually. The only thing is that pi of c is not one of the braids that I know already. So far, I only knew pi of a and pi of b. And what I'm doing here is computing pi of c. But the way that I do it is I have to write c in terms of a and b. And so that's exactly what I did. So I computed it, and pi of c is b bar, a bar, c bar. Okay. I don't think so. Because remember that to multiply, you put to multiply a and b, you have to put a in the bottom and b on top. So this is ab, and this is ba. It's always the same issue when you multiply permutations. You just have to remember which one goes first. Okay. I think this is right. So let's go back to where we were. I'm giving you a general construction, so this is the example. But hopefully you see what I'm up to here. First, I define some set T, and then for each element of my abstract Coxeter group, W, I'm finding a very concrete permutation, sign permutation inside T. And I'm going to think that these sign permutations are going to represent my abstract group W. Okay. So I told you which T. I told you how to find WS inside S sub T super B, the hyperoctahedral group. But the main question that you should have is, why does this work? Right? I'm giving you some construction, but the third and most important question is this really a copy of W comma S? And what I claim is that what I did here is construct for you a way of assigning an element of W to each element of W, an element here. I claim that what I constructed here is an injective group homomorphism. So it's an injective group homomorphism. So what that means is that each one of these guys gets mapped to a different guy here. It is a group homomorphism, and that means that I have really found an isomorphic image of W inside here. Yeah? So W is isomorphic to pi of W, where pi of W is a subgroup of STB. This is my plan. I need to prove all these things to you. But what I claim in this example is that if you operate these elements, E, A, B, A, B, B, A, A, B, A, you get the same thing as if you operate these permutations. Okay. So for example, since AB times BA equals the identity, that's going to mean that this guy times this guy equals this guy. So these guys really do realize this group. Any questions so far?
About 50.
Yeah. Give me one. No, really. Ask me some questions about this.
So pi of W is a normal subgroup?
Pi of W is a normal subgroup.
Of SFSU.
Exercise.
should be by the first, by isomorphism. The groups.
Kernels are normal, but images are not necessarily normal, right? I don't think that's true in general, but I'm not ready to say that I'm sure.
Can this be called a sign system?
People just call this a set of sign permutations. Give me some questions about this construction, really. I mean, I should say this is a pretty abstract construction that you should really take your time to digest and make sure that you think about this example carefully and really multiply some wires and everything. But is the general plan clear of what I'm trying to do? The general plan is I'm mapping each element of my original Coxeter group to an element of a hyperoctahedral group, so that instead of multiplying abstract Coxeter elements, I can multiply in a combinatorial way because I know how to multiply permutations. Okay. So I'm just going to rewrite in the language of a proposition what I just said here, and in the meantime, think of questions and ask me questions, really. I'm very serious. I can guarantee that you're not the only one with questions, whoever you are. If I start with a Coxeter system, I build its set of reflections. What I claim is that the map that takes a generator of my group W and sends it to an element of the sign permutation group extends uniquely to a group homomorphism, which is injective. And like I said, these are a lot of words which exactly mean that this construction that I performed over here really behaves well. So these permutations are really a model for the group. Okay. So let me give you any questions. Let's also discuss this on the forum. I mean, I'll also give you time to phrase the questions that you have, and we'll talk about them.
So we really need this relation that our generator squared are the identity.
Yeah, we need a bunch of things. So let me give you an outline of the things that we need to do to prove this. So we need three things. The first thing that I need to do is actually show to you, which I haven't yet, that when you construct this thing pi sub s, so to each generator s, we associate a sign permutation, but I haven't shown that this is a sign permutation. We saw that here they were a bar cb, c bar, no, c, b bar a, but in general, this is a sign permutation. when I prove that, I will have proven that at least this map really goes from the generators to STB. So that'll be my first step. There's a second thing that I need to prove. Okay. And the second thing that I need to prove is basically that, I mean, this talks about how you define pi on a generator. So that was this step where I defined pi A and pi B. Now I need to talk about how we extend that to the other elements of the group. For example, when you do this after class and you draw these wiring diagrams and you multiply these permutations, you're going to find that you get the same answer, and this shouldn't be black magic. We really have to understand why that is, yeah? So why is it that pi A, pi B, pi A is the same thing as pi B, pi A, pi B? It better be, or else this is not a model for the group. So we need to prove that that's the case, that whenever we have a relation of the form S prime to the M equals E in W, then that generation better hold, that relation better hold with these permutations also. So we need to prove that. Okay. Now, you'll see that because of a problem that you have in your homework, once you prove this, you've proved almost everything here. Because one of the homework problems says that once you have a relation like this, in other words, once you find elements of a group that satisfy the same relations as the Coxeter group, then you have this for free. Extends uniquely to this, which is a group homomorphism. Okay, so once you prove this statement B, you have almost everything. There's only one thing that I haven't underlined, I think, which is injective. And that's the third thing you have to prove. So this, let's see. This is how I plan to prove this. Okay. I actually think that I don't have enough time to do a good part of this, so maybe I should delay this until next time, and we have a couple of minutes if you guys have any sort of questions about this. So let's not rush this and just ask me some questions. Yeah?
For the purpose of this class, is there a distinction between presentation and representation?
Yeah, and not just for the purpose of this class. So representation, maybe you've...
Group homomorphism is representation, right? Basically.
No, so there's a different notion of group representation, and that is a way of representing a group as a homomorphism into a general linear group, which is different. Okay? So that's very different from when I use the word presentation here. I've talked about it as just presenting the group in some way, either as generators and relations, or presenting it in terms of permutations, or just any way of telling you, here, I introduced to you a group. Okay? And representation is group representations are a different topic that we're not actually going to cover in this class.
But it seems to me that this signed permutation, I mean the SNV, is a representation because of the group homomorphism, injective group homomorphism, right? On the other hand,
it's true. I shouldn't say we aren't going to talk about group representations because we are implicitly, and this implicitly is a group representation. But I should just say that I'm not going to talk about the theory of group representations. And if anybody wants to go into this further, I'll be very happy to help you with a project or.
Yeah. The reason is because the title of the class is called Coxeter, representation of groups.
Yeah. So.
But you have been basically doing presentation. That is, you have some kind of abstract group represented as matrices or generators and relations. So there's a presentation, right? And this is the first time I hear that there's a representation.
So I guess you didn't receive some of my communications that I sent about this.
Yeah.
Unfortunately, when we tried to change the name of the class, it was too late. But this class is not a class in group representations.
Yeah.
That was just the most accurate name in the catalog. But
okay.
I think we should stop there. I'll stick around for questions. And do I have office hours right now? I think I do. Yeah. So.
Polynomial type or undecidable? No algorithm. See, that was the problem. I knew that I had. I didn't even know to ask the question.
Yeah, I'm just like, oh, this is not good.
But once you fix the group, but if you know something, luckily my class is here in the bungalows right here behind the building. It's like 2 minutes to walk, 50 feet.
Oh, okay. You can't manage that. Put you down.
That's right.
So, 5 AFC.
That's right. High. Oh, this is undecidable in the sense of logic. It's not easy. No, sleep trying to write last night. Wow.
A better association is between